Recording in progress.
Okay, so we'll start again. About time. Okay. So this shows like how when the particle diameter, because we already see that with decreasing the particle diameter, that really reduce the contribution to the anti-diffusion and also to the non-equilibrium mass transfer. Okay, so and then so that's why that greatly reduce that the plate height. So and then that's why you can see with dp here, this one shows with dp decreasing from 44.7 to 34 and then to 8.8 to 6 micrometer, and then so this h decreased a lot, right? Decreased a lot. So and then so that means like from 4 and I think here even decreased about 10 times. So and also this one you can see that. So because of 1 centimeter, remember I just mentioned, if you look at that one, so for an LC, the optimized one may have here, so about 1 millimeter per second, okay? So because we see that for gas chromatography, so if it's just 2 centimeters per second for 2 meter long column, so that takes about 1.7 minutes. So, but actually in reality, the GC column is 30 meter long, and then so optimized flow rate. So the flow rate used is just about 30 centimeters per second, right? Okay, so that is pretty fast. But for HPLC, like say, if we're using an optimized flow rate at 1 millimeter per second, even you're just using a 25 centimeter long column, so which is a normal practice, and then so for the solvent to go through, it takes about 4.2 minutes, 4.2 minutes. So that is too long, right? So that's why. So and practically, so people using like at least 2 times so the optimized flow rate to do that. I will see that. So and for this one, this is the shows R. R here is not the particle diameter. Okay, dp is particle diameter. Now I'm talking about so this column radius. Okay, we can see the this is column radius. Yeah, so the reason for me to put it here is like say I just want to point out like say, and this is the optimized flow rate. So this one is also proportional, inversely proportional to the radius so of the column, especially like for the capillary GC, because you have normally, because when we talk about the flow rate, you normally will say 1 milliliter per minute, okay? Or we talk about a flow rate, the Q, like say we can in a milliliter per second or milliliter, say per minute, like in this kind of like say unit. So here is the milliliter, not is a linear rate. So that's why. So when the column radius, so when this one, you can see that when the column radius decrease, because that equal to, because this flow rate equals to what? Equals to the area, okay, of the column cross section times. So this linear velocity, right? Okay, so that means when the radius decrease and then the area decrease, and then so, and this one, so the optimized linear flow rate increase. So that's why you can see here, that shows you when the radius of the column, so cross-section decrease, and we can see what happened. What happened is that say, so the optimized, so mu, so increased. So from this one, this location, so to here, so it's increased, okay? So that's the point to mention that. Okay, so I just want to show you. And this one also shows the comparison of the HPLC to GC, and also we compare. So like for the GC, for this two, for curve D and E, what happened, this one is capillary GC. Okay, so we can see this is exactly what I said just now. So for this capillary GCD, so it has the column radius. So this is capillary column is 250 micrometer in the diameter. And then so radius, sorry. So and then so this one, the E, it has a smaller radius, and then so that means it has smaller cross section. So if it has the same flow rate, and then so that means so this one will have faster, so mu, right? Okay, so that's the reason. So when for this part, we can see when the radius decrease, and then the mu kind of increase. Okay, and then how about here? So here we also compare A is HPLC, so it's a packed column, 5 microliter. And then so we can see compare A with GC. So here is the flow rate, optimized flow rate, so of the HPLC, which is about 1 millimeter per second. And then and this is so rate for that, so GC. So this is actually here, so about 30, or here one is about 30. And this one is about, because even smaller, because this is the one we commonly use, about 30 centimeter, that one. And then even smaller, very thin one, so it can be several hundred, 200, like that one. Okay, so, and another idea to show this one is that you can see, so because of the second term, so that B term can be glowed, so in HPLC, so that's why the plate height, theoretical effective plate height of HPLC is much smaller than that of GC. So here is a GC. So oops. So here is the HPLC. Okay, first, plate height much smaller, and second, the optimized flow rate is much smaller as well. Okay, so just give you more comparison of that. And then in general, so we say we can ignore the B term. So, and we have the A term and C term. So that's why. So when particle diameter increase, let's fill in the blank. So what happened? So, and with this one, then A term increase, okay? And also C term increase. So therefore, H increase, right? That's true, okay? So, and that's why. So the plate height is smaller for smaller value of the dp. So that's why in the past several decades, so the HPLC, so manufacturer kept decreasing the diameter dp of the packing material, so for LC column, and that dramatically improved the separation efficiency of LC, and that drives the development of UPLC, okay? So, and that's why I said, I just mentioned UPLC, now I see UPLC. So this is a 10 micrometer particle. This is 5 micrometer particle in 1980s, and then move on to 1990s, 3.5, and now move on to 1.7 particle. What can you see? With decreasing dp, and so plate height decrease at same time, mu optimized. So this one, so increase. Later on you will see that, because actually, so mu optimized flow rate, linear flow rate, is equal to 3 dm divided by, so dp is inversely proportional to dp. So when dp decrease, mu increase. So we can see that. So this is a linear velocity, millimeters per second. But when we set up the flow rate, we normally say milliliter per minute. So that's why. So here, that's why you can see. Here shows you if you have different radius, if a different radius of the LC column. So here we get inner ID, so it's 2 times the radius, okay? If the inner ID, so of the column is 1.0 millimeter, And then, so here for UPLC, another point you can see, for UPLC, you can see here in this area, it's almost flat, right? It's almost flat. So here, so compare with the traditional conventional HPLC, its linear velocity already greatly increased from about 1 milliliter per second to about 5 or 6. And also we can see that if we like increase this linear velocity, so that does not really influence the H that much because this area is so flat. That means the C term, C mu, this one has a less influence. So on the H, right? So here. So that's why, so for UPLC, so you can even using the higher flow rate that is optimized flow rate. And then, so once you know this optimized flow rate, how can you set the linear velocity? How can you set the column flow rate? And then you have to times the cross section of the column. See that? So that's why. So, and for the singular column, and then so that Q, so that flow rate in milliliter per minute will be smaller. And then if you increase the diameter of the column cross section, and then so that's why this one is bigger because it's area times linear velocity, right? Okay, so area of the column cross section, okay? So, and if it's 4.6 milliliter one, and then you have to set the flow rate to be 3.5 milliliter per minute, okay? But normally, what we have, most we use like 2.11. So this is a very common one. So, and then, so you just set like, say, if you're using a velocity at 6 milliliter per second, so in the program just said it's about 0.9 milliliter per minute. Understand? So that's the reason I'm pointing this out. Okay. And then again, we see this one again. We see that. So if we summarize what we have learned, so and so we can see that so the plate height so is smaller for the smaller velocity, okay, because the C term, right? Because H equal to what? A plus B plus C mu. So if this term now in HPLC, we can ignore this one. So if the velocity mu decrease, of course, then H will decrease. Understand? Okay. So, and also H is smaller for less viscous mobile phase. Why is that? Because remember the C term here, we can see for C, for the moving mobile phase, and then for the stagnant mobile phase is proportional to what? dp square dm, right? Remember? You still remember that? So if we go back to C here, mu, sorry, divide by dm. So tp here, mu and dm. So sorry, so divided by dm. dp squared times mu divided by dm. So that's why. So you have a larger, so dm, because less viscous, that means higher diffusion coefficient. So that means the larger dm will get smaller C term, right? Okay, so then H is better. And then the H is smaller for small solute molecule, because the small molecule, anion molecule, the larger diffusion coefficient, again, is of a C term. And also, so the plate height smaller for higher separation temperature, because when we increase the temperature, the larger diffusion coefficient and the less viscosity. So that's why. So if you can see that, so, and this exactly shows, so when the temperature increase, and then how does that influence the retention? You can see that, so when temperature increase, so the retention will be decreased. That means the K value will decrease at 1 to 2% per degree. That means they elute faster. And you can see here at 25 degrees C, the peak well separated. So, and so when it's like increase from 25 to 45, and the retention time for the peak elute at 22, this one now elute at 13, okay. So it reduced, so a lot, right? Okay, so that means much faster now. So from that, we can summarize. If we want to increase the column separation efficiency, that means the larger M value. So, and how can we do that? That means we want to reduce H, the effective plate height. The most practical way is to use small column packing particles, right? So this is how they develop UPLC. Decrease DP, okay, that is very good. And then how about with slow movement of the solvent through the column? That means, so decrease mu, but at the same time, you have to think about, then that will take your longer time for the separation, right? Okay, so this one is something compromise. And then so solvent, so that are in the long viscous as possible. That means the diffusion coefficient. Let me see. I have some number I wrote somewhere. Let me see. Yeah. So normally when we talk about the viscosity, so it's in the unit of centipoise. This one is the centipoise, and 1 cp centipoise equal to 1 times or 1 minute 1 times 10 to the minus 3 Pascal seconds. This is for information, okay? So we can see that if it's at 25 degrees C for your information, okay, for your information at 25 degrees C. So water, the value for that one is 0.894. So CP, so and centipoise, and acetone. So for acetone is 0.306 for that value, and for methanol, which is 0.544. Okay, so and it's better like say you have using solvent, so like non-viscous as possible. But for that case, and then so water seems not really a good one. But well, we are not really just thinking about this viscosity issue. We're also thinking about other things like solubility and then whether it's compatible with the column and so on. But if we just look at this one, the term so the organic solvent, acetone and the methanol, they have a smaller viscosity value than that, than water. Okay. So, and high separation temperature for this one, do you really want to adopt a really high concentration? Oh, sorry, high temperature while you're running separation? Not really, okay? So we can think about it. And the longer columns, although longer column can increase the number of N, but at the same time, increase the separation time. And also we have to think about the increased pressure, okay, backup pressure. So this one, so that is the, although theoretically, so we can think about, so improve the N number in these 5 ways, but so they have their own limitation, right? Okay, so the smaller DP is the most effective ones. And let me think about, let me show you, so the influence of increasing temperature. So the increasing the temperature, so it can speed up the separation, but it also has some disadvantage. For example, so the solvent or sample component, so may, if those the thermolabile one, so they may decompose, right? Okay. And also the vapor pressure of a solvent rises. So when you heat them up, so the vapor and some evaporates and then increase the risk of the bubbles in that detector. When you have the bubbling detector, remember I mentioned that last week, and then you see quite noisy baseline, and then so it's possible to some small ones serve as seed, and then so even green, bro, those big ones, okay? So so ghost peak and so on. And all the chromatography equilibrium are temperature dependent, particularly so all ions, so in equilibrium, so within the aqueous mobile phase. So for that one, so this is the particularly matter for the reverse phase and ion exchange chromatography, and then so that's why. And it makes them the reproducibility not really that good. And solubility of silica is greatly increased in all mobile phase at temperature it rises. Remember, so for the stationary phase, so even for partitional chromatography, even though the stationary phase, the thin layer of the organic, they are chemically bonded to the support, which is a porous silica particle. Okay, so you don't want so those support, solid support silica particles, so they kind of dissolve, right? Okay, and the maximum temperature is around 120 degrees C for silica column, and then should not be more than 80 degrees C for the chemically bonded phase. So that's why in most practice we see many of them just like operate at room temperature. In some cases, you can see the separation based on operated at 50 degrees C, but so, and this is the up limit. It shouldn't, for those partition chromatography for chemically bounded phase, should not more than 80 degrees C, okay? So that's all what we talk about for those like column efficiency influenced by those three processes, okay? And also what can we do to increase the N number? Actually, besides those three thermodynamic and kinetic process we just talked about, so there are other parameter that can also increase, so make the column, the peak broadening, which is the actual column volume, which is also known as the dead volume, so in LC. So in liquid chromatography, actually significant band broadening sometimes occurs outside the column packing, okay? So this kind of like say actual band broadening, so they occurs when the analyte is carried through open tubes, okay? What is open tubes? These open tubes are those, so in the injector, okay, found in the injector system. So those are the capillary that connects between injector and column. So those are capillary between the column and detector, those tube, open tube. And also refers to the volume of the detector cell and the volume of all these connecting fittings. So these are called the actual volume, actual column volume. And some dead volume may cost when analyte pass through all these open tubes. So open tubings, let's say, in this region. So, and for that one, so we only count from the injector to the detector, including both injector and detector. So for volumes of the system, which is before the injector and behind the detector, they are not included. They are not considered as the extra column volumes, okay? Because your sample inject into the column, into the injector, and then it got detected. Your signal already obtained. So in a detector period, that's it, right? Okay. So, and so we have to pay attention to that extra column band broadening in LC. So that means you have to really minimize so this kind of dead volume. And as mentioned, it's mainly due to the flow distribution in the open tube. So that is what we have seen that before, right? So hydrodynamic flow, this one. So because the one, so in the middle is faster than those flows, so along the inner wall of the tube because of frictional forces, right? And the contribution of this actual column effect to total plate height can be estimated using this equation. So where R square, R is the radius of the tube, of course, because the wider the tube, so the larger space, and then so, and there'll be more difference between the middle and along the edge, right? And velocity of the linear flow velocity that matter, as we just mentioned, because you get the compound got longer time, more time to diffuse to equilibrium. So, and then so when the flow rate, when the linear velocity decrease, it has longer time. And then the larger diffusion, and then so, and can help diffuse this one. So that means you have to use thin tubing and less tubing as much as possible, okay? So this actual column broadening can be very serious we're using a small bone column, like those we mentioned about 1.0 millimeter one. Remember it here? We provide you guys several, see? Especially for those very small ones, okay? That'll be more serious, okay? And for those thin ones, for those ones, so therefore, so the radius of the actual column component need to be reduced, and then so we try very hard to keep them as low as possible. Okay, so you can see the actual column volume, so they will make the peak broadening and also cause the peak tailing. Okay, so peak tailing is like that one. This is a nice peak shape. So Gaussian peak, and this is the peak tailing. And then we call this one peak fronting. But when you see the peak tailing, not all just because of the extra column volume. So they can be caused by other problems while you're running the LC as well. So you have to really diagnose. If you see the peak tailing, yes, there are multiple possibilities. You have to diagnose to see it. So what exactly is that one? So it may be the calling itself become function not really that good. So it's not functioning quite well. Or maybe it's because that you inject too concentrated sample. So the colon is kind of overloaded. So you don't want to inject too much, right? So also like say, maybe it's because of the poor solubility of the sample in the mobile phase. You have to make sure your sample can well dissolve in the mobile phase. And then so maybe it's because of the secondary retention, right? Okay, so there's some active site. So in this absorption chromatography that can also hold so your sample by another separation mechanism, like secondary retention. So and so on. So this is something you think about. So and when you do the diagnose, you have to try to see whether if you change the mobile phase or if you change another column, does that help? Okay, and then so if we see if you're using like change the using some buffer solution like adjust pH, does that help? Because that one can help sometimes make you like say make your compound neutral compound or charged compound. So and to avoid some of the secondary or unnecessary so absorption on the column. Okay, so that's all for the first part. So now we're going to start the second part. Okay, so we already talked about the overall so for this LC. Okay, so now we're going to go through some details and talking about the adsorption and partition chromatography. Okay, so ready? So let me expand it. So as I already mentioned, the HPLC include adsorption chromatography and partition chromatography. So for adsorption chromatography, the stationary phase normally is solid. And the separation is due to a series of adsorption, desorption step. Okay. And for the stationary phase, if the adsorbent, so that means the stationary phase is polar. Normally what we use is silica particles or alumina. So then like dissolve like, so the polar analyte will be more likely to retain in the stationary phase. So the polar analytes such as carboxylic acid, so alcohol, and also amino, so they'll be retained. Okay, so that's for adsorption chromatography. And most of the cases, so silica, we say alumina silica, they are common stationary phase. So even though so there are a range of modified surface has been evaluated, and of those silica particle is the most often used, is more used because it has higher sample capacity. And so a wide range of the useful form, so its surface can be modified. You can see this is silica particle. So it has siloxane, so silica, LC, and silica, and it has the OH group sticking out. And the distance between these two, so hydroxy group, so that one is the 0.5 nanometer. So, and this is how those compounds so get absorbed on the adsorbent. You can see because here is polar, right? OH, that is polar. So that makes this polar stationary phase. Oops, sorry. So, and so that's why when it's retaining the polar function of the species. So the compound, if the molecule, they have several functional group, then will be properties. For example, if it's the alkane, so if it's a carboxylic acid, which has the alkane moiety, the alkane tail, and also the COOH group, for example, if it's so carbon 4 carboxylic acid, or if it's carbon 7, so carboxylic acid, so it has the carbon chain. Okay, so this carbon chain will put it outside, and then it will be the polar functional group, so that swap to the stationary phase and do this separation. Okay, so this is to that. And if a solute have different degree of attraction to the phase, and then so different analytes have different, some is stronger attracted, the other maybe not strongly attracted, and then they can achieve the separation. So this is for adsorption. And for the adsorption, it depends on the polarity. So that's why. So its K value, that means the retention factor increase in the following order. So you can see the more polar one will have higher affinity to a stationary phase. That's why. So carboxylic acid has higher retention to stationary phase than amides. So then sulfur oxide, then alcohols and amines, then aldehyde and ketones, then nitro compounds and ethers, and then aromatic, and then etc. hydrocarbons. So this one generally describes the polarity, of those functional group. Obviously, so this carboxylic acid is the most polar one, and then so the saturated hydrocarbons, the least polar one, right? So the polar one preferred. And the separation of adsorption chromatography is easily affected by water content, okay? And the reason for that, sometimes people see like 4 to 20%. 4 to 20%, oops, percent of water at silica is actually get a better result, okay? Get a better result. So it's better than the highly active, the silica. The reason is not really clear, but it's mentioned that probably it's because of either the deactivation of the strong sites on the silica particles, so which may give a very slow desorption rates for some of the active compounds. And then so maybe it's because of the capillary filling of the small number of very fine points, because we know, like say, as we just mentioned, you think about that one, we say the porous, because the silica particle, they are the porous particle, okay? And then so it has maybe the water, so, and then so they just like fill in some of the very fine points, and then so, and that kind of like say prevents some of the mass transfer into this segment, so mobile phase, and then so that kind of like help to lower that C10, right? Because not really necessary to diffuse in. And then so, and anyway, so adsorption chromatography, because of this one, it has some problem with this retention reproducibility, because of like the water content influence, and then other things influence, and sometimes it has some reversible adsorption happen. So that's why nowadays it has been greatly replaced by partition chromatography, and partition chromatography is the more popular one. but still, so it has its own usage, own application. Especially, it is pretty good for the separation of those isomers. Okay, and also, it's when you are handling some compound, so that not really suitable. So there, those compounds that are suitable in non-polar solvents, you may want to think about the absorption chromatography as well. But anyway, it's not really the mainstream. So, and this one just show you a typical application. So for this absorption chromatography, so it's separating the two isomers like this one. So this is trans and this is cis, and then you can see in normal partition chromatography, they may be quite difficult to separate, but here we can see, so they're well separated from each other. Okay, so and for partition chromatography, this is one we often use. So, and the separation is based on the solute partition between two liquid phases. So one liquid phase is a one cell chemically bounded. So on the supporting silica particle, the other in the mobile phase, we say the two liquid phase should be immersible, same as we do, let's say, liquid extraction and partition. So partition utilize the ability of analyte to distribute between the two phases, which is similar to the partition coefficient in this liquid extraction. So the partition chromatography based on the distribution of the analyte in mobile phase and in the station phase. So one thing, of course, that play a role is polarity. So it really depends on somehow, so it's not really the only reason, but it's one of the key parameter. Polarity of the analyte, polarity of the stationary phase, polarity of the mobile phase. Kind of really influence its distribution, the distribution of analyte among between stationary phase and mobile phase. So, and normally the analyte has high solubility. In the stationary phase, we have a high partition coefficient. That means it has a larger K, right? So if it has high solubility, and it will have the better K, right? Retention on the stationary phase. So if it has high solubility in the mobile phase, and then, so that means it has a smaller K value, right? So, and the partition method is more versatile than absorption chromatography because now the stationary phase is chemically bounded on silica particle, and using different chemical reactions, we can make our stationary phase, right? So you can just make your own one. So the liquid stationary phase, so which is the one coated on the silica particle is used, and then in ion chromatography is the polymer, okay, it's a resin, okay, not silica particle, but for normal reverse phase and say normal phase one. So porous silica particle is the most commonly used. So liquid phase is at very beginning, early stage is physically absorbed, but then it found that it has those limitation because this is if it's physically absorbed, and then you have to do the stationary phase coating from time to time, so which is quite so inconvenient, right? Okay, so and so that's why later on have chemically bounded stationary phase on the support. So, and chemically bounded phase is highly stable packing, so that it should be insoluble in the mobile phase. Okay, so and the support for the majority of the bounded phase, stationary phase, is this one. It's the rigid silica or silica-based compositions. Okay, so we can see, so there are this kind of supports that are formed by uniformed, porous, mechanically stable silica particles. Okay, they normally have diameter of like say 1.7 for UPSC and 3, 5, or 10. We say you have to be uniformed because we want that small nominal value. Remember the A term proportional to lambda dp, right? So that's fine. So and the surface so of those, this one, the silica particles, so they often is like say fully hydrolyzed silica particle. So they are just like hydrolyzed by heating with 0.1 mole per liter of hydrochloric acid. So it's just about heat them so for a day or two and to make sure so they are fully so hydrolyzed. So they makes them a very chemical reactive the standalone groups. Okay, so these are the groups. So later on, so they can be used to have the chemical the bounded so functional group on it. So and we can see so therefore so normally for you to generate the chemically bounded stationary phase, we just have reaction of the standalone group. So with those organochlorosaline. So how does that react? I see the typical silica surface including about 8 mmol per square meter of hydroxy group. Okay, so and this total surface area for that. And we can see this reaction going on. This is similar group. So react with this organochlorosilane. Okay, and here's a methyl group, methyl group. This is the functional group you want to chemically bound it. And then so this is organochloro. And after reaction, it formed this so siloxane. Okay, silicon O silicon. So this is siloxane. So and with the function group here. And then, so the functional group, as we mentioned, so last week, so it can be carbon 4, carbon 6, carbon 8, and carbon 18. So if that is case, so this is non-polar stationary phase. And then, so this is a reverse phase stationary phase, okay? So it's called reverse phase. So reverse phase stationary phase is less polar so than the mobile phase. In the mobile phase, for the reverse phase chromatography, we're using water, methanol, acetonitrile, THA, and so on. So that's what we use. Well, when you are doing this one, chemical bounded, because remember, I just want to show you guys here. There's a reason I showed this picture. No. Yeah. You see that? So the distance between the two standalone group is just 0.2 nanometer. So it's, I mean, like say, it's not really a very wide distance between these two, see? Okay, so therefore, not all this standalone group, OH group, they can be chemically derivatized, can have those functional group. So normally at the most, only 50%, of this OH so still get derivatized, and then only still have like 50% of this OH group, like say, remaining there. So what happens? What happens is like say if it has you have like say C18, so coated, it's supposed to be non-polar, but now you still have so at least the half of side still have the OH like sticking out. So that makes a part of it like say polar. They may have the secondary retention. So to kind of help to solve this problem, so that's why. So after this chemical reaction, derivatization to derivatize chemically bound, so this stationary phase, like functional group onto the silica particle, and then so the siloxane, this packing material is further treated, so by the chlorotrimethansine. So it's further reacted with. So this is for information. With 3 methane group. And then because although say maybe the gap between them, steric hindrance may be problem for C18 because C18 has 18 carbon. So it's a large one. So it's really hard to get derivatized. But for methyl, so for methyl group is small enough. So it would be able to replace this active hydrogen here and make it to be, sorry. And then, so make it to be O and then methyl, okay? So by doing so, so it's helped to cap the remaining active site. So on this reverse phase column, and then so to reduce so this kind of secondary adsorption. And then nowadays, 75% of the work in HPLC is reverse phase chromatography. The reason for that is because now for the reverse phase chromatography, it can handle polar mobile phase. And the polar mobile phase often use what? Water. So water can use as a mobile phase. And because of the sample, that means the sample can dissolve in water. So that means because in many of the biological samples, so they dissolve in water, and water is inexpensive and UV transparent, and then and compatible. We mentioned about many of the biological samples, and it's quite rapid for this to easy to use it. And also the mass transfer is quite rapid with this non-polar stationary phase. So as its solvent equilibrium after the gradient elution. So that's why. So reverse phase chromatography is the most popular ones. Okay, so we can see that this one shows the influence about different coating, so on the retention factor. Okay, so here, this is a series of compound, and then phenol, so which has OH here, right? So nitrobenzene, which has an O2 group here. So here's the toluene, so which is the least polar one. Okay, so that's why toluene comes out last. Okay, and no polar ones comes out first. And then here, just like say methyl, R equal to methyl, R is methyl, and say R is C8, and now R is C18. Okay, so we can see that with the stationary phase become increasing carbon chain, the polarity decrease. The stationary phase become even more less polar, and then so that increase the retention of the non-polar compound, right? Because they have affinity to that. And also another thing you should know is that with increasing of this carbon chain, so it's actually also permit use of larger samples. So increase the capacity as well. Okay, so for example, the maximum sample size for a C18, so packing is roughly double of that for the C4, so carbon. Okay, so for the C4 carbon. So that is the common sense for that. And the mobile phase again, normally is water mixed with organic solvent like water with ACN, water, methanol, and later we talk about how we can play with that. Okay, so and here this is how that happened. Now we talk about for the normal phase. Now we just look at the reverse phase. Now let's look at the normal phase. We mentioned actually a little bit so last week as well. For normal phase here and reaction again, so the on prime, so it can be either the cyan group or it can be the amino group, and then it can be the diol group. Okay, so diol is just like say 2OH group. Okay, so and then diol group, and this one, so the cyano group, this one, the polarity of the packing so vary over a considerable range, and the cyano group, this one is the least polar, and the amino group is the most polar one. Okay, and the diol packing one is intermediate. And for normal phase, we know the stationary phase is more polar than the mobile phase. So that means it will retain the polar compound, right? And then so for this mobile phase is often hexane. Hexane, the function of hexane in normal phase is similar to the function of water in the reverse phase. The reason is hexane is almost a very non-polar, right? Okay, and water is the most polar one. Water is more polar than any of those polar functional group we mentioned about just now. It's more polar than carboxylic acid on that functional group. Okay, so later on we talk about polarity index, we will see that. Okay, and other polar solvents, other commonly used solvents, that's polar one. So in normal phase, alpha as ether and methylene chloride and chloroform. Okay, so you can just play with them and then to adjust the polarity. And this is what we talked about actually last week. We want to mention that. So we can see for normal phase, if we have the three alanine, A polar than B, polar than C. And because this normal phase, the stationary phase is polar, and then the polar compound, we have strong affinity to the stationary phase. It will come out last, okay? And then the non-polar one will come out first. But when we change the mobile phase from low polarity, for example, if we're changing from hexane to methylene chloride, So what happened? The polarity index increase, become more polar, and then so that makes A more soluble in the mobile phase, and then so that's why it can comes out faster. So that means when solvent polarity increase, and then how about the K value? Increase or decrease? The K value decrease, right? Okay. For the reverse phase, we see the other way. For the reverse phase, because the stationary phase is nonpolar, so it will keep the nonpolar compound, which comes out last. The polar compound comes out first. And then, however, when we are changing, for example, from water to just like say ACN, and what happened when we change it from water to ACN? So, and then the solvent become less polar. And then for this less polar compound, it has a better solubility now in the mobile phase, and then easy get eluted. So that means for reverse phase, when P polarity decrease, and then we can see the K decrease, right? So P means the polarity of mobile phase. So mobile phase P, not amyloid, mobile phase P, okay? Mobile phase P, understand? So, and the reason for that is because this idea, this concept is related to what we are going to talk about later on. So when we try to choose the solvent for the mobile phase. Okay. So wow, that's a lot of information. I guess it's pretty enough for you for this period of time. So, and how about we take a break again? So for 5 minutes, we come back at 9:01, and then so we'll continue talking about this one. So, and we'll finish at 9:40, okay, because we only have to take 5 minutes break.
Recording stopped.